a bold vision. When a bold vision is pursued, inevitably a tough challenge will follow. Like Christopher Columbus when he sailed westward, trying to find a new way to India. They did not know exactly what lied ahead of them. Or John F. Kennedy when he said, "We choose to go to the moon not because it is easy, but because it is hard." This accelerated the Apollo program. And also the scientists who try to answer the universe's most difficult questions, they work with these really big particle accelerators to find these very tiny particles. All three of these examples are bold visions that then faced very tough challenges. And these challenges, the payoff is not always fully clear, and high risks are at stake. For these challenges, they have the ability to transform the world. Christopher Columbus, he found a new continent. And the Apollo program, not only did they put humans on the moon, no, they also made the integrated circuits more popular. That is what we have now in our computers and our smartphones. And the scientists at CERN, who work with these really big machines to find these very tiny particles, they invented the World Wide Web, which is now the internet. So what about today? Also today, we face very difficult challenges coming from bold visions. One of these could be to make humanity a multiplanetary species, to venture outside of Earth, discover the solar system, and settle on other planets, to install permanent cities there that are self-sustaining and can look after themselves. That is, for example, such a city on Mars. To make this possible, asteroids could be a very nice resource for materials. To venture outside, humans, when traveling in space, could really use minerals, metals, and water, which these asteroids would provide. Asteroids are sort of the building blocks of the solar system. And at the moment, we do not really have a way to move around on these asteroids in a controlled way to explore them. However, it would be very important to know so, like going somewhere where we specifically want to find a nice material that could be used.
In the past, whole nations would invest billions to solve a problem like this. But due to technological advancements of the past decade, now it is actually possible to do this at a university level. This is where project SpaceHopper from ETH Zurich comes in. We are 10 students who set out the ambitious goal of building the first asteroid rover. So this isn't the kind of rover that you may know from Mars, like this one. Because asteroids have a way lower gravity than, for example, Mars, wheels, for example, are not possible because they would simply slip, they would lose traction. Also, asteroids have very irregular environment, so a wheeled system could easily get stuck. Here, for example, you can see how a Mars rover gets stuck on Mars. This problem is even worse on asteroids. So as you can see, an asteroid rover cannot have wheels. But a system like this has never been built. So it is, in the beginning, really just a wall of a challenge with so many unknowns, and you really don't know where to start. And this is really what our talk is about, these challenges and how to overcome them. So first what we do is we analyze our problem. And after we kind of have an overview of what we're actually facing, we really try to break down our problem into kind of smaller sub-problems. And then these smaller, maybe a little bit easier problems will be better to tackle. And in our case, we had to first find out how do we move on an asteroid. So we have to find a way, how do we move? And the next thing is, how do we control the movement? It's not easy. And after we found that out, we have to find a way to test a system that was built for asteroids on Earth, which is an extremely hard challenge in of itself. And if this wasn't hard enough already, we also have to think about the fact that this robot will have to be launched on a rocket, so it has to fulfill certain criteria for that. So now that we know the sub-problems that we have to face, we can go on to try and find solutions. So for this, we look through the literature, see what has been done, try to gather as much information as possible. But at the same time, it is also important to look beyond the classical literature, the classical examples, to really have your eyes open for inspiration from all kinds of places. And then, if we have done that, we are ready to really find good solutions for our problems. So in our case, we had to first find a way, how do we move on an asteroid? And as I already mentioned in the beginning, wheels will not work. So we looked around, what other options do we have? And we realized that robots with legs actually are very good at the kind of environment that we see on asteroids. So that is like irregular, unpredictable environments. And so we decided, okay, I think legs will be a very good option for our robot. So our robot has legs, as you can see. Then the next question was, now that we have legs, how do we use them? Do we just walk, like here on Earth? Or do we do some other kind of motion? And here we actually found some inspiration, and we found it from the Apollo footage on the moon. So in this picture, you can see an astronaut on the moon, and you can see now how he is not walking, but he's actually jumping on the surface of the moon. And you can see that humans intuitively figured out that actually, when the gravity is lower than on Earth, so for example on the moon, it is more efficient to jump than to walk. So we found that now on asteroids, the gravity is even lower than on the moon, so this effect is going to be even more strong. So our robot is not walking, but is actually jumping or hopping, just like the astronaut in the video. Now, the question is, how do we control these jumps? I mean, if you jump and you slip a little bit during the jump, the robot will start to tumble, it will lose its orientation, and if you cannot control somehow the position of the robot, the orientation, then it will crash, and then it's just not going to be controlled in any way. So to solve this problem, we're looking for inspiration. And the inspiration for this we actually found in the animal kingdom. So we were studying how cats jump, and we were studying their behavior, and from this we learned what we do. Okay, maybe not exactly this jump, but look at the picture at the video right here. So you see how the cat is falling, and it's twisting and it's moving its legs in such a way that it can land in a normal fashion. And our robot actually behaves very similarly. So since our robot already has legs, why not just use them also for reorientation during jumps? We would save weight for other systems that would otherwise have to do this job with something that we already have. And so we decided that, yeah, we're going to use the legs of our robot to reorient during jumps. So the next question that arises from that is, okay, now we know how we want to use our legs during the jump, but the question is, okay, how do we control the legs to actually behave like a cat? It's not very easy, right? And to do this, we also need some innovations, and here we really found a solution with artificial intelligence, because we can actually train our robot in simulation to jump basically like a cat. It really learns to do that in simulation. We train it in simulation, and then this behavior that the robot learned on the computer, we transfer it pretty much on the real robot, and with some little tricks, the robot in real life behaves like the robot on the computer. It displays its learned behavior and jumps or reorients just like a cat. So with all of these things now, with all of these solutions to these core problems, we designed the actual system. So in the back, you can see a render of the system, or on the picture, and here you can actually see the real system. So this is our robot, and now you can see, oh, there's actually 3 legs. So the question is, why do we have 3 legs, not 4 or 5 or maybe 2? And the reason for this is basically, as I already mentioned, this robot will have to go and be launched on a rocket. So it has to be small, it has to be light, and it has to be compact. And we found the best solution to be still a capable system that can use its legs during jumps and still be small and compact is 3 legs. So it's a really unique system that it has 3 legs. And next up, you can see how the robot in simulation, so this is the environment that we use to train our robot, and you can see how the robot jumps and uses its legs to then land again upright and then even jump again. So this is how our robot would behave also on an asteroid. So now that we have that out of the way, the question still is, how do we test a system designed for an asteroid? So on asteroids, the gravity is extremely low. How do we test such a system on Earth, where the gravity is a lot stronger? This in itself is a very big challenge, because you cannot just turn off gravity because you want to test something. So you have to actually design specific tests in order to kind of simulate a low gravity environment. So again, we apply the same principle as before. We take our challenge and we divide it into smaller problems. So in our case, we want to test the functionality of the robot. That means we want to test the main functionalities, so the jumping and the reorientation. And so we designed specific tests for that. For the reorientation, we built kind of a gimbal setup, like for a camera, where you want to stabilize a camera. So we fix the robot at a certain position, but allow it to rotate freely around its axis. And with that, we can see here a simulation how the robot is trying to reorient to a horizontal position using its legs. So this is a simulated setup, and in the future we will test this on a real robot. So now for the jumping capability, we built kind of a pulley system, so where the robot is attached to a rope that has a counterweight attached to it, so it offloads some of the weight from the main body, and it allows it to jump in such a way as if there was low gravity. Here you can see a video of that test. So you can see how the robot just jumps up. And in the future, the goal will be to test both of these capabilities together, so the jumping and the reorientation. And this will probably be in a zero-G flight, where we can really simulate low gravity and kind of turn off gravity for a moment a little bit.
So, what does this all mean to you here today? Maybe at some point in the future, one of your grandchildren could travel in space to another planet or to such another city and depend on the resources that are harnessed from an asteroid that could have been explored from such a robot that we are developing now. Still, this robot, SpaceHopper, could be used in the future and in the not too distant future for a pure research and science mission, because it is so light and so small. And also, the costs for rocket launches are steadily decreasing. Still, to the people who say we should rather spend all this time, effort, and money put into developing systems like this, should be spent on problems and challenges that we face here on Earth. We say to you, sure, problems and challenges here on Earth are very important to be tackled. Still, we are convinced that some part of this effort, even if it's not so large, should always be put into bolder visions. Because when we humans face tough challenges like human spaceflight or flying to other planets, which are very difficult, great innovations and nice feats of exploration turn out of it. So, life is not only about everyday problems. We should always be inspired by the future and our exploration to drive forward. Thanks for listening.